Okay, so I'm going to start by just finishing up the tail end of yesterday's material. So we were working with this theory of n by n Hermitian matrices phi, and we're studying this with n large and with this 't coupling g squared times n small. And yesterday we discussed the computation of the leading order exponential decay of the two-point function, the retarded propagator, but we didn't discuss the growth of the squared commutator. So it's convenient to define a double commutator in this way. So this is an average 1 over n to the fourth times a sum over four matrix of two pairs of matrix indices of type of regularized product of commutators. It's regularized in the sense that we've split up the thermal density matrix e to the minus beta h into two factors. Those two factors are sitting between the two pairs of commutators in this product. And that can be computed using the following contour in the complex time plane. So we insert the phi I prime j prime operators either at plus or minus, one of them at either plus or minus I epsilon. We take the difference of these. That gives a commutator with this operator that's inserted at time t. Then we have a period of Euclidean evolution in time that corresponds to one of the factors of e to the minus beta h over 2. And then we have another commutator with the second operator inserted at minus I beta over 2 plus or minus I epsilon. That gives the commutator with this operator here. And then we insert another piece of Euclidean time evolution that takes us down to time minus I beta, and we impose periodic boundary conditions. So this is a time contour that computes this quantity. And again, we should think about integrating interaction vertices over the contour. Now, in the free theory, the answer to this, for this quantity would just come from a product of retarded propagators. One for this commutator and one for this commutator. That would be a diagram that we could draw like this. These are both retarded propagators. And in double line notation, we would have the following. Since we're summing over these matrix indices, we would have a double line diagram that would look like this. So in particular, we have two index loops. So that would give us a factor of n squared that would partially cancel the 1 over n to the fourth. And we would find that the answer was proportional to 1 over n squared. That will be true of the perturbative corrections which we consider. We'll consider planar perturbative corrections. So everything will be proportional to 1 over n squared. Now, to compute this thing at leading order in the 't coupling, what we would like to do is we would like to get the exponential growth to leading order in a 't lambda. And anticipating slightly, the behavior that we're going to find is something like something times e to the lambda squared times t. In order to get this behavior, we'll have to resum an infinite set of diagrams, all powers of lambda squared times t. One source of diagrams that contribute at this order are just self-energy corrections to these propagators, like the ones that we discussed yesterday. Those can be summed in a simple way by just replacing these retarded propagators by their dressed or renormalized expressions. Those things are decaying exponentially. So in particular, that won't lead to the exponential growth that we're trying to find. The growth comes from a different set of diagrams, things that are called ladder diagrams, where we add what are called rungs for an obvious reason. And we can have any number of these rungs. So let's look at one of them. One rung comes with two interaction vertices. So it comes with a factor of lambda squared, 1 lambda for each interaction vertex. But it comes with a factor of t because intuitively we can integrate this rung anywhere along this ladder. And the ladder runs from time 0 over here to time t over here. So these ladder diagrams will contribute powers of lambda squared t. And in order to sum all powers of that quantity, we'll have to sum all of the ladder diagrams. Summing ladder diagrams is something that comes up frequently in perturbative quantum field theory, and there's a nice trick for doing it. This is a very typical trick. What you do is you define something to be the answer you want. So this shaded blob is supposed to represent the sum of all ladder diagrams. And then you notice that if you take the sum of all possible ladder diagrams and add one extra rung to it, you get basically the same thing, but now you no longer have a term with 0 rungs, so you have to add that one back on by hand. So we have this identity. This is the same kind of identity that you use in high school to sum the geometric series. Here we're interested in the late time behavior of this function, and for large times, this product of retarded propagators isn't growing. In fact, it's exponentially decaying. So we can ignore this term at late times and solve a homogeneous equation that says that taking our sum of ladders and adding an extra rung to it doesn't change the sum.
Excuse me, where are your external lines attached to your diagram?
Yeah, the external lines are just at these points. So there's one point here, one point here. Those are the top two here. So it really looks like this ladder is sitting right here. The external points correspond precisely to the arrangement of the points on this diagram. Okay. Now, solving this equation, this homogeneous equation, is not something that can be done analytically. The technique, well, you do it in momentum space, and you can do some of the momentum integrals by hand, but you're left with a one-dimensional integral equation in momentum space that has to be diagonalized numerically. And the result of doing that is the following. You find that C of t and x for large times is growing like 1 over n squared. This is the 1 over n squared that we discussed a second ago, times an integral t through k. Okay, so this coefficient a of k here cannot be determined using the homogeneous equation. You would have to solve the full equation, but it won't matter very much as long as we assume that it's smoothly varying at k equals 0. And this lambda of L is like a momentum-dependent Lyapunov exponent.
You could probably argue that it's smoothly varying at 0, right? By just looking at the...
Yeah, it's smoothly varying at 0. Yeah. So the important thing about this Lyapunov exponent lambda L, I don't really have room to write it here. Lambda L of k can be expanded for small k as lambda L with no argument. That will be the value at k equals 0 plus a half times k squared lambda L double prime plus higher orders in k. And the important point is that this guy here is positive. And it's equal to some number times the Atrophic coupling squared divided by beta squared times m. And this term here is negative. So the Lyapunov exponent is positive for small k, but it's decreasing a little bit with k. For large times, this Fourier transform will be dominated by the term that's growing fastest, so it will be dominated by small k. So we can do the Fourier transform in a Gaussian approximation. And we find in position space, this is like, well, we have a of 0 over n squared. Okay, and I've defined a parameter VB, which is built out of lambda double prime and lambda L. So this is the result of the computation, and this is valid at large times, but not such large times that the whole term here becomes too large. So it's valid at order 1 over n squared, but for large times. 1 second, let me, okay. So to understand the meaning of this expression, well, okay. Remember that this theory contains elements both of this k-local behavior, sort of at a given site, because the matrix interactions involve many degrees of freedom coupled together. And it also involves elements of locality in space. And both of those features are on display in this result. So let's set x equals 0 and study the function we're at the same point in space. Then we have exponential growth divided by n squared. So the double commutator starts to become large, let's say of order 1, at a time that's logarithmic in n squared, the coefficient determined by lambda L. But for larger x, we have to think about the behavior of this function in spacetime. So let me try to draw a picture of the locus where this whole term starts to become of order 1. That would look something like the following. It's some kind of hyperboloid like this. So this is space, this is time, and outside here, c is small. And the idea, although this calculation doesn't demonstrate it, is that inside c would everywhere be of order 1. All we can really see from this calculation is that it's starting to grow close to this locus. Asymptotically, this is linear, and it's linear with time t equals x over vb plus a constant. So we have this linear emergent light cone that was characteristic of local theories. But at smaller distances, we have this exponential behavior, and in particular, the separation here at x equals 0 is like 1 over the Lyapunov exponent times log of n squared. So one final comment about the form of this function. It looks like a sort of weird combination of exponential growth and diffusion. So you can think about this function as a solution to a PDE, which is like a heat equation plus an exponentially growing term. So we have both diffusion and exponential growth. Diffusion by itself normally leads to things that are spreading diffusively, not ballistically. But if you combine it with exponential growth, you get something that travels ballistically. That's this linear behavior here. And apparently, the mathematics of that type of equation is similar to what you find for describing something called a traveling combustion wave, or an explosion. It's described by a combination of exponential growth and diffusion. So these out-of-time order correlators, or double commutators, are sort of weird. They're, in many senses, unphysical, because they involve operators out of time order, and in order to measure them, you would have to be able to run the system backwards in time. Some people have discussed experimental protocols for doing that, but it's clearly a little bit unphysical. But the payoff is that in that weird unphysical world where you're allowed to run time forwards and backwards, the butterfly effect is very much in your face. And associated to every simple operator is this traveling combustion wave, like an explosion of influence of this operator everywhere in space-time. Okay, there was a question earlier? Yeah.
I just wanted to know, so lambda L of k, how does it behave for large k?
Yeah, that isn't known. So the only computation that's been done of this. And so the K dependence of lambda L was worked out in a paper by Chowdhury and Swingle. And they did it numerically, and I think they just studied it for small values of K.
Okay, so you're approximating this flow, which is over all K, like
Well, that's because we're taking t to be large. So think about this integral when t is large. Then it will be dominated by the region where the exponential growth in time is fastest. And lambda L of k is maximal for k equals 0, or at least it's locally maximal. So the integral for large time will have a saddle point for k close to 0.
But you do need to argue there's not some other maximum at finite k or something.
Yeah, and well, that argument hasn't been made, but it seems quite plausible. Yeah. No, it's not. Well, it's reliable for arbitrarily large t if you're content to just discuss the 1 over n squared correction. But if n is finite, then higher orders in 1 over n will become important at times that are probably logarithmic in n squared. We'll see examples of how that works in the gravity discussion in a moment. Yeah?
Did you assume something about beta or m?
No. Sorry, I think that's, let me remember. Yes. This statement here is true when beta times m is small. And there's a more general expression for finite values of beta m, but it approaches this for small beta times m.
What's the value of VB?
Unfortunately, the numerics that the group I mentioned before did wasn't extremely confident. They weren't extremely confident in their value of VB, but it seemed to be close to 1. Actually, it seemed to be, in their computation, slightly big. It was extrapolating to something slightly bigger than 1, which seemed like a problem. But they didn't make a very precise statement about that. I don't know. I can't determine it from this argument, but it shouldn't depend on n, and apart from that, I don't know. Okay, so that's the end of yesterday's lecture. So now we're going to start on holography. And as Aaron Wall mentioned, okay, yeah, one more question.
Yeah, so how sensitive is it to relations operators? Say, looking at the quantity of, say, traces of powers of the
Yeah, it shouldn't depend on that. You should get the same Lyapunov exponent for anything like that. Basically because you would have, well, yeah, let me not try to give a careful argument for that right now. Yeah. Okay, so in one of Aaron Wall's lectures, he mentioned that in some respects, black holes are similar to ordinary thermal systems. He used the example of a lump of coal. And the ADS-CFT correspondence, of course, makes this precise. We can think about ADS-Schwarzschild black holes as describing a thermal state of a holographic theory. And you guys, I'm sure, know this by now, but let me just state it. There are sort of two important parameters to keep track of in the relationship between the bulk and the boundary theory, at least in the most classic example of the n equals 4 super Yang-Mills theory. So in the boundary theory, we have an important parameter n squared. N is the rank of the matrices. And so this is proportional to the number of degrees of freedom at a given site in the theory. And this is related in the bulk theory to 1 over the Newton constant. So when the boundary theory is at large n, the bulk theory has small g Newton. It's very weakly interacting. And the second important parameter to think about is the Atrophic coupling lambda, which is related to 1 over the string length to the 4th power in the bulk theory in ADS units. L here is ADS length. So when the boundary theory is strongly coupled, strongly interacting, then strings are small in the bulk, and we can use a gravity approximation. So that means that in the limit where the black hole and the fluctuations around the black hole are described accurately by gravity, we're thinking about an extremely strongly interacting theory with many degrees of freedom. And so that should be like textbook quantum chaos. So in the remainder of the lecture today, we're going to discuss how black holes manifest the properties of chaos we've discussed so far. So these very simple manifestations, the decay of the 2-point functions and the growth of these double commutators.
Is it still chaotic for finite n?
Yeah.
Because yesterday you intuition that for weak coupling, it takes longer for it to use its energy, but now it's strong coupling.
Well, for large but finite n, then we could still discuss the same quantities. For really small n, then we don't know how to do the calculation in the bulk, and probably the boundary analysis would be, the answers to things would be qualitatively different there as well. Okay, so we're going to start by discussing the 2-point functions. So the idea here is that the 2-point functions in the black hole background decay because stuff can fall into the black hole and it doesn't come back out again. We're going to discuss this in quantum mechanical bulk. So the correct description of stuff falling into the black hole is using the formalism of quasi-normal modes. So we're going to discuss that topic. And first, a tiny bit of setup. So here's the Penrose diagram for an ADS Schwarzschild black hole. In Schwarzschild coordinates, the metric looks like this. For the moment, I'm going to discuss a spherical black hole. So this space is a sphere. This is a d-2 sphere. Capital D is the space-time dimension of the bulk theory. And f of r is given by this expression, where capital R is a length scale which is related to the horizon radius, but it's not the horizon radius. The horizon radius is determined by solving f of r equals 0, the largest r such that f of r equals 0. Okay, and what we'd like to compute is a 2-point function in the boundary theory. So we'd like to compute something like 1 over z of beta trace something like this. And actually, we're going to discuss, it's slightly simpler to discuss the retarded propagator, where we consider a commutator of these operators. But the 2-point function can be recovered from the retarded propagator, and the analysis is simple. But for concreteness, we're going to consider this quantity. Now, if these are local operators, then this thing is related to a limit of bulk correlators. in this geometry of a commutator of bulk fields. Where we have to multiply by a factor of r, and there's also another coefficient we should multiply by. But the limit isn't so important. We could consider versions of these operators that are smeared out in spacetime a little bit, and then we would be considering a bulk correlation function of these operators at finite radius. I should have drawn on this diagram the following. So a constant r surface would look something like this, and constant t surfaces within this wedge look something like that. So what we're interested in computing is a two-point function between a bulk operator here and a bulk operator here, as the time separation between them becomes large. Okay. So the idea for doing the computation is the following. In the large n limit in the boundary theory, the bulk theory is weakly interacting. In particular, this will be a two-point function of free fields, of free quantum fields. And those satisfy the wave equation as an operator equation. So this correlation function satisfies the wave equation up to coincident point singularity. And in fact, this is a retarded propagator for the wave equation. So we should discuss some properties of the wave equation. So for example, one could consider just the massless wave equation. D squared phi is equal to 0. And it's convenient to consider this with a change of variables. Where we study a particular spherical harmonic with angular momentum L on the sphere. Then we have a function psi of t and r, and we removed a trivial factor of r. The point of doing this is that this equation now becomes the following. It looks like an ordinary flat space wave equation with a potential, where this coordinate r star is called a tortoise coordinate. And it's defined by r star is defined as the integral Okay, and the point of defining r star is just that in terms of this variable, we have a simpler differential equation. It's a differential operator in space. So look at this formula here. Because f of r behaves like r squared for large r, this integral is convergent, so it makes sense to put one of the limits at infinity. But at the horizon, f of r vanishes, and we have a logarithmic divergence there. So r star is equal to minus infinity at the horizon, and it's equal to 0 at infinity. It runs between minus infinity and 0. I can sketch a picture of the potential that we get as a function of that coordinate. So here's v, here's r star. This is 0 over here, this is the boundary, and the horizon is over there. The potential vanishes at the horizon and has some kind of behavior like this. It diverges at the boundary, it vanishes at the horizon, and it has some kind of behavior that depends on the angular momentum. But for reasonably large angular momentum, it has a well-defined bump like this at an intermediate value of r. So the idea behind the decay of the two-point function is that the solution to this equation is like starting out with some configuration where the field is supported in this region out here. And as time evolves, the field will be able to leak into the region where the potential is 0, and the field will just propagate forever towards the horizon. That's the field falling into the black hole. So the amplitude to remain out here will be decaying exponentially in time, and that describes the decay of the two-point function. So that's the physical picture. The mathematics of this is described by what's called quasi-normal modes, and they are solutions to a sort of funny boundary condition for this differential equation. The boundary condition that they're a solution to is where you write psi of t and r is equal to e to the minus I omega t, and then you try to find a function of r so that it satisfies the equation. And you impose the boundary conditions that psi should vanish at the boundary at r star equals 0, and also that it should be purely infalling at the horizon. That means that it should be proportional to e to the minus I r star plus t times omega in the 0 potential region over here. So those are a pair of boundary conditions you could consider. Because we're imposing two boundary conditions, we only expect to have solutions for a discrete set of frequencies. In fact, those will be complex frequencies. They'll be complex frequencies that have negative imaginary parts, so they'll lead to exponential decay in time. Now, why should we solve that problem, and why should those determine the decay of the retarded propagator? Yeah?
I might have missed this. Where is that peak at the short?
Where is what?
The peak, the maximum.
I mean, this is at some radius that depends on the angular momentum, but it's outside the horizon of the black hole at some intermediate radius. If the angular momentum is 0, the picture doesn't look like this. There's no, it will be a monotonic function, but it's the same formalism applies. Okay, so to justify why these frequencies are relevant, we can use a general formula for the retarded propagator for the wave equation. So the retarded propagator satisfies that equation with a source at coincident points in space-time. And if we consider the retarded propagator in frequency space, so in frequency space for the difference of time arguments, and then as a function of r star and r star prime, a pair of spatial coordinates, then this will satisfy that equation with a source, with a delta function source, when r star is equal to r star prime. So we'll have a second order equation with a delta function source. By integrating that equation across the source, you find that the retarded propagator has to have a discontinuity in its first derivative, with a unit discontinuity in its first derivative. And we can write, but that it should solve the wave equation away from the point where r star is equal to r star prime. And we can solve that equation in general in the following way. I'm going to write this, and then I'll explain what the symbols are. Okay, so what are these symbols? Chi left and chi right are solutions to the wave equation with fixed frequency, and they're solutions to different boundary conditions. Chi left is a solution which is purely ingoing at the horizon, but no particular condition at the boundary, so we can solve that equation for any omega. Chi right is a solution to the problem where we set the value at the boundary equals 0, but we make no particular demand about what happens at the horizon. Again, we can solve that equation for any value of omega. W of omega is the Wronskian of these solutions, so W of omega is equal to chi left prime chi right minus chi right prime chi left. This is independent of R star. R star is equal for the two, but it's independent of R star by the wave equation. Okay, and you can check from this that this solution is continuous, but it has a discontinuity in the first derivative, which is by this amount, and that's canceled by the denominator. So we have a unit discontinuity, and this is indeed a solution to the right equation. The boundary conditions that we described for chi left and chi right ensure that this is going to be the retarded propagator, as opposed to, for example, the advanced propagator. Okay, now we can understand why these quasi-normal modes determine the decay of this function. So we think about Fourier transforming back to time, dt minus I omega t times gr of omega, and also with the radial coordinates, this is gr of t. And we can take this contour over omega, and we can deform it into the lower half plane. And as we deform it, we will pick up singularities at the poles of this function. The poles of 1 over w of omega occur when w vanishes. And the Wronskian of a pair of solutions vanishes when those solutions are the same. So we pick up a pole whenever there is a solution to both boundary conditions. So generically, there's not a solution to both boundary conditions, but when there is, there's something that's both ingoing at the horizon and 0 at the boundary. Then we have these two are equal. The Wronskian vanishes, we pick up a pole. That explains why this weird set of frequencies determines the decay of the two-point function. Yeah?
I think the integral should be the omega.
Thank you. Okay. So in general, finding the quasi-normal modes for a particular black hole background is a difficult problem. It's actually not even super trivial to do it numerically. But there are some solvable examples. The basic solvable example is, one is the ADS2 black hole, which is really the same as a piece of global ADS2, and then you can use conformal symmetry to solve the wave equation. And the form of the boundary correlators that you get looks like this. Where delta is the conformal dimension of the boundary operators related to the mass of the bulk field. And we can expand this thing as e to the minus 2 pi t over beta times delta times 1 plus a correction term from the other term in the sinh. And we have all integer powers of this quantity appearing. So the spectrum of the frequencies for this case is actually purely imaginary. So this is for the ADS2 example. But more generically, the frequencies will not be pure imaginary. They'll have both a real and an imaginary part. The imaginary part is always negative, of course, so we get decay. I put another example in the homework. This one is pretty easy to at least write a simple equation for the frequencies. You have an infinite potential for x greater than 0, and you have a delta function spike at some negative value of x. You can write an equation involving trig functions that determines the quasi-normal frequencies, and you can solve it in limits, or you can solve it numerically by plotting in 2 dimensions. The final comment I want to make about these quasi-normal modes has to do with the behavior for large values of L, large angular momentum. So in that case, this angular momentum barrier here gets very large. And it's very hard for the field to tunnel through the barrier and fall into the black hole. That leads to an imaginary part for the quasi-normal frequency that's exponentially small. It's determined by a WKB, like a tunneling calculation through this angular momentum barrier. It's like exponentially small in the angular momentum. The picture that goes along with that is that there are modes on the black hole which correspond to things that are basically just orbiting the black hole. And in order for those to fall into the black hole, they have to tunnel through the angular momentum barrier, and that's very slow. So we think about the 2-point function as diagnosing thermalization. There's something sort of weird about this, that in this very strongly interacting theory, there are still these modes with high angular momentum that are thermalizing extremely slowly. They're happy just orbiting the black hole for a very long time. I don't know the answer to the following question, but it seems interesting to ask what happens to that at weak coupling. Is there any version of that statement in weak coupling? Okay. So that's it for the 2-point function. The physics of the exponential decay of the 2-point function, stuff falls into the black hole, and the mathematics is these quasi-normal modes. Actually, maybe one other thing I'll mention is that the way we've discussed it, it sounds like every different bulk field will have its own set of quasi-normal modes. And that's a little bit in contrast to the statement in classical physics that these Ruel resonances are the same for any functions in phase space that you consider. And I'm not totally sure about this, but it might be the case that if we consider finite coupling corrections in the boundary theory, or possibly even finite n corrections, that the bulk fields will be able to mix with each other in such a way that only one set of quasi-normal frequencies will determine the very late time decay of the fields. But I'm not completely sure if that's correct. Okay, so let's move on to discuss the out-of-time order 4-point functions. By the way, I'm not mentioning references too much in this talk, but I've put a page of references online, and I think they're linked in the schedule. So for example, this discussion of quasi-normal modes in the context of ADS-CFT was introduced in a beautiful paper by Horowitz and Hubany. And I encourage you to read the paper, it's really nice. But I put a bunch of references there for the material in the first 2 lectures. So let's now discuss the out-of-time order 4-point functions. So I think, yeah. Sorry, I couldn't hear.
What's beta?
In this expression? Yeah, that's the inverse temperature. So this was for this answer was for a ADS2 black hole, which has some temperature, and beta is 1 over the temperature. Yeah.
Clarification question. So for large L, you said that thermalization happens very slowly.
Yes.
The first equation that you wrote down, that trace of ES to minus beta H O comma O, is given by this 2-point function in the black hole background that already assumes thermalization, doesn't it?
No, that just assumes the ADS-CFT correspondence. The relation between the boundary operators and the bulk fields is just the ADS-CFT correspondence. And yeah.
Because the CFP is in a thermal state. And you
Oh yeah, so we're computing, you can discuss thermalization, you can discuss thermal states even for theories that don't thermalize. So for a free theory, we could consider the thermal state. And then if you consider two-point functions, you'll find that they're periodic in time, they're oscillating. They're not exponentially decaying. And so for this thermal state, many perturbations decay exponentially quite rapidly with a time scale determined by beta. But high angular momentum modes decay very slowly. So they thermalize very slowly. But that's a statement that can be made just about perturbations to the exactly thermal state. Yeah, in the discussion of thermalization, people sometimes also discuss different types of probes. Like people sometimes discuss what's called a quench, where you start from a state that's very far from thermal equilibrium, and then you evolve it forwards and see what happens to it. And there, yeah, so here we're discussing something which is in some ways a little simpler. We're starting with the thermal state, and we're just pinging it slightly with one low energy operator, and we're asking what happens to that tiny perturbation. Okay, so let me continue with this topic. I think that last week, every single speaker used, in a fairly significant way, the fact that killing time translations in a black hole background correspond to boosts of the Rindler region near the horizon, correspond to Lorentz boosts. And that fact sort of comes to life in the discussion of these quantities. And I want to just review it with a slightly different emphasis. So let's imagine that we have the two-sided equilibrium black hole, and we zoom in on a region near the bifurcate horizon. So this is a region where a flat space approximation to the black hole geometry is good. Let's imagine that we have some spaceship which is accelerating to stay outside the black hole. It's following a trajectory that looks like this. It's a constant Schwarzschild R trajectory. And let's imagine that at time t equals 0, the spaceship has been holding onto some particle, and it just releases it. The particle no longer accelerates. Instead, it falls into the black hole. It follows a trajectory that's initially tangent to this world line. So we'll follow a trajectory like that. Let's compare that to what would happen if the spaceship had released a similar particle a little bit earlier. So some time delta t earlier down here. Then that particle would also be released tangent to the trajectory, and it would follow a trajectory that looks like this. So it would be, in this frame, very close to the horizon. Now, these particles don't intersect each other. But if we could imagine that for some reason we were supposed to follow this particle backwards in time, and not back into the spaceship, but just backwards along this trajectory, then these trajectories would intersect at this point here. And there, without doing anything fancy, we can compare the relative boosts of these two particles. So we can compare the difference in rapidity of these two particles. And that will be a rapidity that's equal to 2 pi over beta times the difference in time, delta t. This is just the statement. So gamma we can think of as rapidity, or we can think of it as Rindler time. And the statement here is the normalization between Rindler time translations and Schwarzschild, or killing time translations, is by a factor of 2 pi over beta. This is actually really the thing that defines what we mean by beta. This is how you compute the inverse temperature of a black hole. Okay, so this fact is going to be important. So before we get into the details of computing these 4-point functions, I want to give a sort of qualitative discussion that is supposed to parallel the discussion we had yesterday of these states that we're perturbing with the V and W blips. So the qualitative discussion will be about doing that in the black hole geometry, where the thermal state is represented by the black hole geometry. So let's start out by redrawing this Penrose diagram. And okay, before we use Schwarzschild coordinates, for this discussion, it's going to be helpful to use a different set of coordinates where this is x plus and x minus. We use conventions where they're equal to 0 at the bifurcation surface in the center of the black hole. So the null coordinates are set equal to 0 at this point. In terms of these coordinates, the metric can be written as and we're also going to stop thinking about a spherical black hole and consider a planar black hole. So we have d minus 2 planar coordinates here. So these coordinates are called Kruskal coordinates, x plus and x minus. So, okay, so here's our equilibrium pure state beta that we started out the discussion yesterday with. And let's build up slowly. So let's think about acting on this state with an operator v at time 0. That will, in the discussion yesterday, that created a localized disturbance at some point in the system. In black hole geometry, what that looks like would be, for example, adding an extra particle. That's like the particle being released by the spaceship. And if we follow the particle forward, it's going to fall into the black hole. If we follow it backwards in time, just considering this as a state and evolving it forwards and backwards in time with the bulk Hamiltonian, then the trajectory will look like this. So this is the complete space-time description of a state where we've made a small perturbation to the thermal state. There's some particle that emerges from the white hole, it approaches the boundary at time t equals 0, and then it falls through the future horizon. Okay, so let's now consider a state where we move this operator backwards in time. We act with it not at t equals 0, but at time minus t over 2. Well, we can translate this thing backwards in time using this boosting argument. And in particular, the trajectory will now be compressed close to this horizon here. So here's the time minus t over 2. And the trajectory will look something like this. It will be close to the horizon. An important point is the following. If we're considering a low energy perturbation to the thermal state here, then in the natural frame of this diagram, the energy and momentum components of this particle will be of order 1. Well, by of order 1, I could mean either thermal or ADS scale. It doesn't really matter which. But in this picture here, we've boosted the particle. So one of its energy momentum components will be large. That's the component which is like the momentum in this direction. This direction corresponds to the momentum. I'm going to use the letter Q for the momentum of the V particle. We'll use P later for the momentum of the W particle. But that's Q in the moving upwards in the minus direction. That corresponds to a component Q minus with an upper index, which is proportional to minus Q plus with a lower index. And this component will be large, of order e to the rapidity, which is pi over beta times t. That's 2 pi over beta times the difference in times. Difference in times was t over 2. So it's of order e to the pi over beta times t. Okay. So next in complexity, let's consider adding a second particle. In order to add the second particle, which we'll call W, and we want to add that at time t over 2, W of t over 2 times V of minus t over 2 times beta. In order to add the second particle, it's convenient to think about this state here on some Cauchy surface which touches the boundary at time t over 2. And then if we're just describing the state at that time, we have a state where there's some particle here deep inside the black hole which has large momentum. And if we follow it backwards in time, it's aimed to come out and hit the boundary at this time minus t over 2. So it's a high energy particle traveling close to the horizon, aimed to just barely make it out of the black hole. So we start with that particle there, and we add the particle corresponding to the W operator, which will be something which is moving in this direction. And by the same argument that we made here, but with the opposite null component, the W particle will have a large value of p plus, which is proportional to minus p minus. This will be of order e to the pi t over beta. So we have two high energy particles boosted in opposite directions. And they're destined to have a high energy collision somewhere near the center of the diagram. It's a high energy collision with a center of mass energy squared that's called the Mandelstam Invariant S. This is basically the center of mass energy squared, which for this problem will be proportional to the product of the large momenta, p plus, q minus, which will be of order e to the 2 pi over beta times t. Again, in either ADS or thermal units. So that's the description of this state here. If we consider the state with the operators in the opposite order, then we'll have the particles approaching the collision from before. So in other words, this state here corresponds to an out state for this high energy scattering problem. And the state with the particles in the opposite order corresponds to an in state for the same scattering problem. So their overlap is basically a scattering amplitude. There's something that I think that's weird about this, because from the perspective of the boundary theory, we're just kind of tooling around with low energy perturbations to the state. We have the thermal state, we're making low energy perturbations by these operators in V and W, but then we're evolving forwards and backwards in time, but nothing too dramatic seems to be happening from the perspective of that system. But in the bulk theory, something crazy is happening. There's this collision that's taking place between these particles with unimaginably high energy if the time is large. The collision energy is growing exponentially. And really crazy bulk things can happen in that perturbation. And that's the bulk description to this seemingly very benign set of operations in the boundary theory. So there's a sense that the boundary theory is small perturbations, but chaotic time evolution is related to this very dramatic effect in the bulk, this high energy collision. I'm not sure I'll have time to comment too much on this, but it's worth noting that that high energy collision contains a lot more physics than is easily diagnosed using the out-of-time order correlators. Those things sort of are only sensitive to moderately high energies. But the actual bulk state contains, for large T, much more exciting phenomena. Okay, so now we'd like to use this qualitative discussion to get a formula for the out-of-time order order correlator using the fact that we have an inner product of an in state and an out state. And for the kinematics that we're discussing, it's it's convenient to use the formalism of the iconal approximation. So this is adapted to problems where you have a scattering problem with large longitudinal momentum, so the particles have large relative boost, but they don't scatter with a large amount of momentum exchange. So momentum exchange remains of order 1, but the relative boost is large. This is the type of problem for which the iconal approximation is supposed to work. And in this setting, it's useful to use the following characterization of the kinematics. So we have this W particle, which is moving this way, and this V particle that's moving that way. And we characterize W by a state where we describe the P minus component and the transverse position. And we describe V by a state where we give the Q plus component and also the transverse position. So we describe the longitudinal momentum of V and its position in the transverse direction, and similarly of W, and similarly for V. The point of doing this is that in the iconal approximation, we have a simple formula for the scattering matrix in this basis. It looks like the following. We have so let me define what these quantities are. S is the center of mass energy squared, that's this quantity. B is the impact parameter, that's equal to y minus y prime. And this parameter delta is called the iconal phase. And it's a bit of a misnomer because in general, delta is a complex number. So the value of this thing, which looks like it should have absolute value 1, can be less than 1. And in that setting, you have in this relation, the states can differ by a state chi, which represents inelasticities in the collision. So for example, the collision could produce some radiation, some gravitons or something like that. Those would be described by states of this form. And the only important thing about chi is that it's orthogonal to these two particle out states. Okay, so we can use this formula to write an expression for the out-of-time order correlator in terms of this iconal phase. The expression would have been super simple if the V and W operators that we applied on the boundary had been nice enough to create bulk states that were in this basis that we use for writing the scattering amplitude. But in general, they're not. So we have to write a formula that integrates over the kinematics with some wave functions. So the integral here runs over all of the variables that appear in this expression here, the transverse positions and the longitudinal momenta. These wave functions are Fourier transforms of bulk to boundary propagators. So when we act with one of these W or V operators on the boundary, we create a bulk state with some particle in it. And in general, that will be a superposition of states like this. The superposition is described by these wave functions. So we integrate so the bulk state consists of a superposition of these basis elements with these wave functions. We have one in state and one out state corresponding to the two different terms there. With the W and V in one order, that's the out state. With the V and then the W, that's the in state. So when we compute the inner product of those, we have an inner product of in and out states folded against these wave functions, and we get this expression here. The inelastic term doesn't contribute because it's orthogonal to the two particle state, which would be the out state. Yeah?
Why is there P minus and Q plus in the end, but P minus and Q minus on the out? What breaks the symmetry between P and Q? Is that
No, where? Sorry.
in your equation, you have
Oh, sorry.
yeah.
Typo. Yeah, I have trouble with pluses and minuses. I like U's and V's, but I think that's not widely, well, I think most people don't, so I have trouble writing things in terms of pluses and minuses. Okay, so this is our formula for the out-of-time order correlator. And what we'll need to do next to understand its behavior is to get a handle on this iconal phase delta of S and B. So our main example that we'll discuss in most detail is the case where we have the elastic iconal approximation in gravity in ADS, for the ADS black hole. And there, delta of S and B is like the following: G Newton times S times e to the minus mu times B, where I'm suppressing lots of unimportant factors like numerical factors, powers of the ADS length, and even powers the impact parameter B. I want you to focus just on these three factors because they're what's most important. So we're going to see what happens when we take that formula and plug it into this expression. But first, I want to show you how to derive this formula. And there are several different ways of deriving it that have been discussed in the literature, and I wasn't really sure which one to talk about. In the end, I decided to discuss the first one, which is due to a tuft. And this one is not, I mean, it's a little bit idiosyncratic, which probably, in some sense, isn't the best way to learn about it, but it's extremely vivid. So I wanted to share that derivation. So the idea behind this derivation of the iconal phase is the following. We think about our scattering problem in two stages. We have a high-energy scattering between V and W particles. In the first stage, we take the W particle and we replace it by a classical gravitational field that's sourced by that particle. That classical field will take the form of a shock wave, a gravitational shock wave that's sourced by this high-energy particle. In the second step of the computation, we study the propagation of the V particle on that classical background. The V particle gets transformed as it passes across the shock wave, and that transformation gives us the iconal phase. So let's now discuss this computation. So we're going to start with the first step, which is finding the classical background associated with the W particle. So here's our ADS Schwarzschild black hole. We're going to consider the case where the time is quite large. Oh. I realized I forgot to say something earlier. Sorry, we'll come back to this in 1 second. The thing I should have mentioned is the following. This left-hand side depends on time. Where's the time dependence in the right-hand side? The time dependence is because these wave functions depend on the insertion point of the boundary operators. And the important thing is that they will be such that the momentum components that are typical in the wave functions will have the behavior that we discussed earlier. So in particular, within the ensemble corresponding to these wave functions, the typical value of p plus times p minus will be of order this. Okay, so sorry for forgetting to mention that. Now we're back to discussing the classical background sourced by the W particle. So it will be propagating close to this horizon because it corresponds to a time that's very late. So it's boosted into a trajectory that is propagating very close to the horizon. And it's going to source a gravitational field that also gets Lorentz contracted onto a region very close to the horizon. So this double line here represents the gravitational shock wave that will be sourced by the W particle. And the idea is that we can solve for the back reaction of the W particle using this metric. This is the original black hole metric, plus a perturbation. So ds squared equals ds squared, the original black hole metric, plus a perturbation, h minus minus of x minus and y times dx minus squared. And in the limit of large time, where everything is compressed, everything is boosted onto this horizon, we're going to have that h minus minus is a shock wave. It's proportional to delta function in x minus times some function h tilde of y. Okay, so before we try to solve for this function h tilde of y, what does this even mean? We have a metric with a delta function component that looks weird. What is the meaning of this metric? So first, away from x minus equals 0, we just have the ordinary ADS Schwarzschild metric. It's just in this region here at x minus equals 0 that something funny is going on. And that funny thing can be described as follows. Let's imagine that we have a light-like trajectory, so a null trajectory that's moving in the x minus direction. And let's ask what happens to it as it crosses this, this region of space-time. So to determine what happens to it, we should solve for the condition that the trajectory is null, so ds squared equals 0. It's traveling in a direction with it's traveling in the x minus direction, so dx minus will not be 0. We're assuming that dy is 0. So we can solve for the trajectory by setting this term here plus this term here have to give 0. And we're assuming that dx minus is not 0. That's the direction this thing is going. So we can factor off a factor of dx minus. And we conclude that a of 0, since that's the value of the product of these coordinates at the location here, a of 0 times dx plus is equal to h minus minus of x minus and y dx minus. So that's the condition that it's null. And we can now take this equation and integrate it. And we can take this condition and integrate it. And we find the left-hand side gives a change in x plus as we cross the shock wave. And the right-hand side gives h tilde of y. So we have h tilde of y. Left-hand side gives, sorry, I should have put a plus here. It was the sum of these two things that was 0, so the equation sets them equal to each other. A of 0 times delta x plus. So the trajectory comes in here, and it comes out over here with a delta x plus. Delta x plus that's determined by this equation. And it depends on the transverse coordinate y along the horizon where the geodesic happens to sit. So this is the meaning of the shockwave metric. We have two pieces of the black hole background, and they're glued together along the horizon with the property that if you come in from one side, you come out the other side shifted in this null direction. So it's two halves glued together by a position-dependent null shift. This type of vector field was discussed earlier, for example, in Aaron's talk and also in Edward's lectures. Here we're gluing the black hole together by that transformation. I find it helpful to draw a different diagram for this black hole that makes the geometry a little bit clearer. So let's first draw the Kruskal form for the ADS-Schwarzschild black hole. So that looks like the following. So the Kruskal diagram, this plane is literally just the x plus x minus plane without any weird conformal rescalings, and the geometry looks like this. So to get the shockwave geometry, we take the region where x minus is positive, and we shift it downwards. We shift it downwards like this. So the resulting geometry, the two horizons no longer meet, and we have a geometry that looks like that. So if you come in over here, now we're using continuous coordinates so that null geodesics, for example, follow these continuous lines, but the geometry itself has been shifted. Okay, so that's the meaning of this shockwave metric, but we need to actually solve Einstein's equations. So this is an ansatz. We've understood what the geometry means. We need to solve Einstein's equations. The component of Einstein's equations that we need is the minus component of Einstein's equations. And it's convenient to integrate this dx minus along the surface where x plus is equal to 0. So we're integrating Einstein's equations along this surface here. And this implies the following. Okay, implies the following equation. There's a differential operator in the, this is just the Laplacian in the transverse direction, and then there's an effective mass term, mu squared. Mu squared is proportional, well, actually, it's exactly equal to the second derivative of the area of the black hole with respect to a radial deformation. So if we move outwards, how does the area change? It doesn't change at first order, but it has a second derivative. It's the second derivative of the area divided by the area itself. That's what this mu squared term is. Okay, and that's acting on this quantity here, which we could simplify just to h tilde, right? H tilde of y. And the expression on the right involves this average null energy operator, the integral of t minus minus across an entire, a complete null geodesic. And this is an example of something that was discussed last week, that the average null energy condition prevents you from traversing wormholes. So the argument is as follows. H plus of y gives us this null shift. And the operator on the left-hand side is a positive operator. Minus the Laplacian squared is a positive operator, and this mu squared is positive. So if this quantity here is positive, which is guaranteed by the average null energy condition, then H tilde of y will be positive. And that means that the shift in the x plus direction will be positive. So we'll have a diagram that looks like this. Notice that with this diagram, you can't get from the right side to the left side through the wormhole. However, if the sign of delta x plus, had been opposite, then this would have been shifted upwards, and it would be easy to get from the right side to the left side. Okay, that's sort of an aside. For our purposes, what's important is that we can take this and we need to evaluate the right-hand side for the case of interest, where we have this W particle propagating close to the horizon. This quantity here just measures the total P minus of that W particle, and this expression gives a pi g Newton times minus P minus times a delta function in the transverse space. Of the following type. So the equation we want to solve is this one. And this will determine the shock wave profile. Okay. Now, I actually don't want to erase this just yet, so let me write the next thing on this board over here. So we can solve this equation. This is like a massive Poisson equation, and we get the H tilde of y is going to be equal to, up to constants, g Newton times minus P minus times something that's exponentially decaying, y minus yw. Okay, and I'm ignoring prefactor powers of y, which are also present in inverting that differential operator, keeping only the exponential dependence on y. Okay, so this completes the first step in Atrophic derivation of this phase. We've solved for the classical back reaction of the W particle in terms of the shock wave. In the second step, we need to study the propagation of the V particle on that background. So we have this shock wave metric, which shifts as you pass the shock wave metric, everything gets shifted over by an amount delta x plus. So if we study the propagation of a V particle with a definite value of q plus, then the phase that we get in passing the shock wave will be equal to e to the, I think it's minus I, but we'll see, times q plus, the momentum of the V particle, times the shift. Okay? And putting in our formula, delta x is proportional to h tilde of y. That's that expression there. I'm going to drop the factor of a of 0, which is at this level an unimportant constant. We get q plus times delta x, which is proportional to h tilde, and then we use this expression for h tilde, g Newton times q plus, p minus, e to the minus mu times b. Okay, and writing the product of momenta in terms of S, that was the formula that we were trying to establish. Yeah?
Was there something special, like why we took the shockwave geometry to be generated by W instead of V? Could we have done the other way around, like taken V as the...
Yeah, this is a great question. So just let me repeat it because it's important. The question is, the procedure that we followed sounded asymmetric. We replaced the W particle by its gravitational background and studied the propagation of V, rather than replacing V by its gravitational background and studying the propagation of W. Well, one thing to note is that the formula that we found in the end was actually symmetric. It was symmetric in V and W. We would have got the same answer if we'd done things in the opposite way. But let me just sketch for you an alternative derivation which makes this asymmetry go away. So the way the alternative derivation goes is as follows. You take both particles and you consider them as sources for the gravitational field, which you treat in the quadratic approximation. So you treat both particles as sources. You solve for the value of the gravitational field. We're using the quadratic action, so this is solving a wave equation. And in this approximation, these sources are these sort of delta function stress tensors, and we find the shockwave solution for the gravitational field, and we just plug that into the Einstein-Hilbert action, evaluate the action. And the answer for the action gives us this, this phase here, this delta. So that's maybe a more sort of obviously correct way of treating this at quadratic order, but you don't get this picture so much of what's happening in the scattering process. This derivation makes very clear what's happening. The particles get shifted over in a null direction by passing the shockwave. Yes?
Your picture on the board doesn't look symmetrical.
Yeah, that's because the picture was drawn in a, this is accurate in a particular boost frame, where implicitly in drawing this picture, I was boosting so that this particle didn't have very high momentum. But the actual picture would be symmetric.
Can you draw a symmetrical version?
Well, a symmetrical version for the back reaction is just yeah, so
And you broke the symmetry by picking which particle.
no, you can draw a symmetrical version for this sort of at linear order in the perturbations, and then we just shift this one also downwards in that way. So we'll have this here, and this will be shifted down like this, something like this. Something like that. So the particles traveling in both directions will fail to cross the wormhole. Yeah, based on this, by the way, one technical point related to this. You might have thought that this is an underestimate of the phase shift because we studied the phase that gets accumulated by the V particle crossing the W shock, but we didn't discuss the phase of the W particle crossing the V shock, so shouldn't the full phase be twice this answer? And the computation involving the Einstein-Hilbert action shows that it's not twice the answer because the gravitational field itself gives a minus one of those two terms. So in that way of doing the derivation, you do have a sum of both phases for the two particles, and then you have minus one of those terms for the gravitational action. So it comes out to the same thing. Okay, I'm out of time, so I'm going to, this is actually a reasonable stopping place. We've got this formula, and we've got the formula in gravity for this phase shift. So next time we'll do the easy part, which is just plugging that thing in and analyzing the behavior in space-time of the out-of-time order correlator. So let me stop there. Thank you.